All right. Thanks everybody for coming to see this talk today. My name is Mike Larkin. I work on the OpenBSD project. I'm a committer there, have been for a number of years. And one of the efforts that I've been undertaking for the last year or so has been to improve WXORX protections in OpenBSD. And that's what I'll be talking about today. So a little bit about myself. I started committing to OpenBSD back in 2008. And the first time I started committing was actually I was working on S3 ACPI support. Show of hands, how many people know what S3 ACPI is? 2, 3. That is a better way to describe that is suspend to RAM. So I was an OpenBSD user, and I was annoyed that my laptop would not suspend when you close the lid. So I posted a message on the OpenBSD mailing list and said, hey, anybody working on suspend resume? The answer I got was a halfway working diff, and hey, go fix this and come and talk to us later. So went and fixed that, got it working on a couple of machines, got that committed over the next couple of years, and 18 months or so, we improved that, and now suspend resume works very well in OpenBSD. In a bar one evening, somebody challenged me to do S4. And people know what S4 is. S4 is hibernate, suspend to disk. So over a beer one night, I got challenged to do S4, and that turned out to take about 3 years. It was much more difficult than I thought. Lately, I've been working on the OpenBSD native hypervisor, which will be coming very soon. That's what says VMM there. It's not in the tree yet, but it's coming. Late last year, I started taking a look at improving WXORX, which is a memory protection policy that we'll get to in a few minutes. And what I did is I thought that would take about a month. And it was a lot longer than that. A couple of other notes. I don't consider myself a security guy. I know this is a security conference, but I don't paint myself with that brush. I viewed my efforts in improving WXORX as a correctness effort. Basically, my philosophy was, if you have a memory configuration that allows writable and executable memory at the same time, that's a bug. It's broken, it's not right, and it needs to get fixed. Now, security kind of falls out of that as a side effect, but I view this effort as a correctness effort, fixing a problem in the tree, fixing a problem in the source code. So for those of you who don't know what WXORX is, it is a memory protection policy. WXORX is not a piece of hardware, it's not a piece of software. You can't point at it and say that's WXORX. It is a philosophy that says memory should not be simultaneously writable and executable. And that sums it up in one sentence. Now, since it is just a policy, you have to actually enforce that policy somehow. And the way that we enforce that policy is by through use of some features in the operating system and some features of the processor. So inside the operating system, we have to make sure that we set the appropriate page permissions so that we don't allow people to create bogus mappings, and that we actually have to depend on the hardware to then go and enforce that for us. So we do both of those in OpenBSD, and just like other operating systems that implement WXORX do similar things. Both user mode, that's processes, and the kernel is also protected in this model. So before this talk, I actually went back into the changelog in the OpenBSD source tree, and I looked to try to identify the first commit where WXORX came into the tree, and I gave up after about 15 years. So it's been in the tree for a long, long time, in various forms. We actually started on a different hardware platform than what I'll talk about today to implement user mode WXORX support. It was actually on the original Spark. That's where we started, long time ago. So the point I'm trying to make here is OpenBSD has a long history with WXORX. It's been in the tree for a while, but the kernel has kind of lagged behind a little bit. Different architectures that we support have different levels or different degrees of support for WXORX. The hardware enforcement model that we use typically takes the form of page table page protections. So when an operating system is managing a page table for a process, it marks the pages with particular permissions. Some architectures that we support have individual bits for read, write, and execute, and others, like i386 and AMD64, have read and write, and then another bit that says no execute. So it's a slightly different permissions model. We use whatever the platform gives us. We do support i386, obviously, and we have for a long time, but our support for i386 actually predates the time at which the processor actually supported the hardware no execute capability. So we've had it in for a while. In order to have i386 WXRX, you need to have a processor that can support PAE paging, which came out with the Pentium Pro. So that was a long time ago. But you also have to have a processor that supports the execute disable bit, and that came in later models of the Pentium 4. That's why we started with other architectures. As I'll talk about today, kernel mode WXRX support lagged behind in OpenBSD for a long time. And it all came about, at least for the purposes of this talk, back in October of last year. So way back in October 2014, I was not a WXRX hacker. I knew what it meant. I knew that we did some WXRX stuff, but I really didn't care too much about it. And when I was reading the commit logs, I came across that commit. Make sure the direct map isn't executable on hardware that allows us to do so. Enforcing WXRX in the kernel like this mitigates at least some ret2dir attacks. That's return to the direct map. It was a security exploit. So that innocuous little change there, which by the way was a 2-line diff, made me think, I wonder if the direct map isn't protected. I wonder what other areas are not protected. And that became an all-consuming effort for the next few months. So I looked at all the other protection bits in the kernel that I could find, and I found a lot of areas that had incorrect permissions or flat out completely broken permissions. And slowly I started picking these off over the next few months. So I would go in and I would fix something, and I would look at the map, and then I would say, okay, now that region's broken, I got to go fix this, and I got to go fix that. And I'll talk a little bit more later about exactly the regions that I found that were broken. So AMD 64 was pretty much done by January or February of this year, but i386, it was a disaster. So 32-bit Intel platform was just horrible. And I didn't actually think I was going to do it. And then there was another beer bet. So a little bit before I jump into how we fix WXRX, I'm going to talk a little bit about how OpenBSD manages memory. And this will just be a few slides talking about how the various modules inside our kernel interact with each other. When a process issues a malloc, or makes a malloc call or an mmap system call, that goes into the kernel, just like any other reasonable operating system. And inside the OpenBSD kernel, we have a bunch of different modules that are present. We have the scheduler and the file system layer and the buffer cache and all this stuff. But there's two layers specifically, or two modules that work together to manage memory. First is called UVM. The other is the PMAP module. So UVM is a machine-independent memory manager. Machine-independent means it's the same code for all the architectures that we support. So the same UVM code runs on AMD 64, and i386, and Spark 64, and all the other platforms that we use. The UVM is responsible for managing things like the page layout. So for example, it keeps track of which pages of physical memory have been allocated and to which process that they're assigned. It also keeps track of grouping pages together. It also manages things like backing files when you mmap a file. It is the high level general for coordinating memory accesses or memory management. Underneath that, you have a module called the PMAP module, or the PMAP layer. And the PMAP layer is machine dependent or architecture specific. So although we only have one UVM, we have one different PMAP for each hardware platform that we support. And that's the thing that interfaces with the real hardware. It's the thing that generates the page tables, writes the permission bits into memory, asks for pages to be validated or invalidated as needed. So we have one of those for each. So as a memory protection policy, WXRX is enforced at both layers in OpenBSD, and that's important. So we make sure, first of all, that when you ask for memory, if it's in the kernel, you can't even ask for memory that's writable and executable. We won't give it to you. We also then make sure that when we put the configuration into the PMAP, that it's done properly, that the right permission bits are set. Another way of saying that is when you ask for a page that's readable and writable, you don't get an execute bit stuck on that mapping. So that's important. As a matter of fact, in our UVM code, It's basically saying here, if you're mapping to the kernel map and you want write and execute, what do? We just panic. That's actually done by design. We would much rather fail early. This is a bug. If you find code that's doing this in the kernel, it's wrong. It's flat out wrong. So what we could do is, like some other Unix-style operating systems out there, we could just printf and say, you've asked for a bad mapping, but what does that do? That's opt-out security. I'm sorry, opt-in security. We have security enforced by default. You can't turn this off. So I don't want to know 20 years later that yesterday I made a bad allocation, because who knows what's happened since then. So this is what happens up front in our UVM layer. If you attempt to do this, you're dead. So now we've talked about all the pieces that are in place to enforce WXRX. So we've talked about the OS support, which in the case of OpenBSD is the UVM module and the PMAP layer. Talk a little bit about the processor. The processor has to support enforcing that those types of memory accesses and those types of memory controls. So now we've got all the tools on the table now to build a WXRX policy engine. Now we have to go find where all the regions are that we want to protect. So now we have the ability to do it, but we haven't done anything yet, and that's where I came in last October. So like most operating systems, the virtual address space on AMD64 OpenBSD is split up into a bunch of regions. And we don't really care too much about the user space region, because that's already done and it's been in the kernel for many, many years. So for this talk, I'll focus on the top layers: the kernel image, the direct map, the kernel space, and the page tables. If you remember from a few minutes ago, there was a commit that already fixed the direct map. So that leaves only 3 regions. That should be pretty easy. How hard could that be? Just to fix 3 areas of memory? If it was only that easy. So first, let's look at the kernel itself. So the kernel is a binary that's loaded off disk during the boot process, and it's placed somewhere in memory. It's placed at the same place in memory every time, but it's placed in memory. And if you look at what is in the kernel binary, there's a bunch of different regions inside, a bunch of different sections: text, read-only data, BSS, symbols, and a bunch of other stuff. This is what it looks like if you were to dump the symbols and look at the different regions. So at the top, kernel text is going to get treated as readable and executable. There's no need for the OpenBSD kernel to write to its own code. The OpenBSD kernel does not do self-modifying code. So kernel gets readable, and the text, which is the code, gets readable and executable permissions. Read-only data, obviously, gets read-only permissions. Not executable, not writable. Data, obviously, gets read-write, but not execute. There's no reason for the OpenBSD kernel to be executing data. That's a bug. And there's some padding at the end where the symbols live, and that gets a read-only treatment as well. Now, the interesting thing about this is that before I started looking at this, we had some breakdowns of individual regions, but there weren't quite this many. And everything had executable permission, which meant your debugger symbols were executable. Your BSS was executable. Your data was executable, and it was completely wrong. Now, again, is it a security thing? I don't view that as a security problem. I view that as a correctness problem. It's not correct. It needs to get fixed. So over the course of a few months, we started down this path of fixing this by subdividing the kernel into different regions and then applying the correct permissions. And this was an iterative process, and it took a couple of months. It took until January or February of this year. So once you've got all that done, basically by the way, the great thing about fixing these kinds of issues, when you turn on your machine and run it, it'll either blow up spectacularly or it'll work perfectly, because if you have the wrong permission, you're going to see it right away. So while I had the hood of the car open, I fixed a couple of other things as well. So if you remember earlier, I talked about how I was involved in suspend and resume and hibernate. Suspend and resume and hibernate need a special piece of code placed in low memory to resume the machine when it first powers up. And the way that we had been configuring that from code that we inherited from somewhere else was everything was just all on one page. So our resume trampolines, that's what the name of the code page is, actually had code and data and stack on the same page. So again, since you got the hood open and I'm working on fixing all these WXRX regions, I might as well fix these too. So I took each of the trampolines and I split it in two pieces, one for data and one for code, protected the code with readx, readable executable, and protected the data with read-write. I also did the same thing for the multiprocessor spin-up trampoline, which serves a similar purpose. Again, previously all these things were read-write execute. Why is that important? Well, it's a place in memory that if you were to view this as a security problem, an attacker could place something there. It's readable, writable, and executable. It's the greatest permission greatest permission of all. Prior to my fixing AMD 64, all of our page tables were executable. That makes no sense whatsoever. So now our page tables are only read-write. They're not executable anymore. Our APIC page was executable. That's the most absurd thing I've ever heard of. That's the interrupt controller. The interrupt controller's registers are mapped into memory, and we were making that area executable. There's no reason for that. So now it's not. And of course, if we miss something, we'll fix it when it becomes known. But I'm pretty sure that AMD 64 is in reasonably good shape now. So the next logical question would be, how do you know you did it right? I mean, I'm talking about just going in and setting permission bits on regions and saying, ta-da, I'm done. There's a couple of different ways. The first way is fix it and then break it. So for every region that I protected, I made a test that said, attempt to go use some permission that region doesn't give you. So for example, I made a module in the kernel that after the kernel code was protected with non-writable permissions, it attempted to go write on the kernel text. And as expected, we blew up. That's what you're supposed to do. Similarly, I attempted to execute a page table, which doesn't make any sense, but previously it would actually try. This time now it takes a fault and exits. So there's all these tests that you can induce on each region to verify that you did it right. There's a couple of other things that you can do. You can actually dump all the page permissions and look at them to make sure that you didn't miss something. QEMU and Box can help you with this a little bit, I found. In QEMU, you can dump what they call the TLB, which is not the TLB, it's really just the listing of page translations. It's a page table dump. For example, a mapping like that says FFFFF 81478000 maps virtually over to that physical page 1478,000. What you're looking at there are the permission bits on the end. So what do you think that says? What does the X and the W mean? It's writable and executable, and that's bad, right? Well, for some reason, QEMU decided that X meant no execute. So that was a little bit confusing for a while. I applied a bunch of permissions and then I went, wait a minute, all of my pages are executable. No, the X there actually means no execute. So you can go into QEMU and you can dump the page mapping of every page in the system, put it into a file, sort it, and pretty easily pick out the regions that are wrong. So we've done that a number of times, and now everything is in pretty good shape. Okay, so in another infamous beer bet, someone challenged me over a beer to fix i386 next, and I should have refused the beer. So the memory map on i386, I don't have a picture of it, but it looks very similar to AMD 64. The kernel regions are fairly similarly laid out. It's smaller, obviously. It doesn't have the direct map, which the direct map is a virtual, it's a virtual to physical translation that has a linear mapping. So what that says is direct map plus 1 equals physical memory 0 plus 1. Direct map 1000 is physical address 1000. It's used a lot in device drivers to allow quick access to physical memory without going through a lot of translation. It consumes a lot of virtual address space. If you have a machine with 16, 32, 64 gigs of memory, it will eat up 16, 32, or 64 gigs of virtual address space. And you don't have that on i386. The address space is too small. The page table is slightly smaller, but fundamentally it's almost the same beast. The nice thing, obviously, about i386, the part we didn't have to fix, is the part that we had already fixed. That was UVM. So if you remember, UVM is the module that does the memory management, and the PMAP layer is the thing that does the enforcement. UVM is one UVM for all the architectures, so all of the improvements that had gone into UVM over the years were applicable to i386 as well. So when I started looking at fixing WXRX in the kernel on i386, the first thing that you noticed right away was that our PMAP layer actually didn't even have support for the NX bit. There was no way to even turn it on. So if you can't turn it on, it doesn't matter what UVM tells the PMAP layer to do. If the PMAP layer can't turn the bit on, you're not going to get that kind of you're not going to get that kind of separation. So what we had to do, the downside of this meant every single page in the system was executable. So the first thing we had to do was fix the PMAP. So the way that you fix that is you shift to a different model of PMAP, and that PMAP goes from each entry being 32 bits wide to being 64 bits wide. So we brought in a piece of PMAP code for PAE that was like 10 years old, and it was super full of bugs and ugly and horrible, and we slowly made that one work. So we finally turned that on earlier this year. One other thing about i386 that you don't really have to deal with on AMD 64, i386, we still have a lot of users that are using old crummy hardware with i386. Stuff that's so old that it doesn't have PAE or doesn't have NX. So what this means is we couldn't just simply take a new PMAP and plop it into i386 and say, here you go, that's what everyone's going to use. We'd have users screaming at us, rightfully so. So what our PMAP code does, it's very interesting. In boot up now, the machine boots with an old style PMAP, the old legacy style. And then we query the CPU to see if it supports the new features. And if it supports the new features, what we do is we take whatever the kernel has done up to that point, this is early in the boot sequence, we create a new page table, copy all the entries over to it, get rid of the old one, and turn on the new mode. So it still allows us to remain compatible with both models. So we figure out at boot which one to use. And obviously, if you have a processor that supports it, now you have a newer page table format which supports the NX bit, and now we can actually start to implement those regions. So I turned that on back in April. We had previously tried in OpenBSD to run a PAE PMAP before, and it didn't work out too well. The goal at that time was to allow like big memory i386 machines with lots of RAM. The new PMAP that I built up earlier this year is really only intended to support the NX bit. It doesn't allow you to have lots of memory on i386. Use AMD 64 for that. Okay, so now we're in a similar situation for i386 that we had with AMD 64. Now we have all the tools available to go and enforce the regions appropriately. Figure out which regions need which permissions. So we're going to go subdivide the kernel like we did last time. So the second time went a lot faster than the second time. i386 went a lot faster than AMD 64 because the second time you do something, you're usually better at it. But I got distracted by working on the hypervisor. So it kind of languished for a while. So we had this new PMAP that was working and everyone was using it in the tree, but we didn't actually protect anything. So I flipped the switch in April, but I didn't actually get to commit the actual final fixes until August. And that's not to say that it took 4 months. It took like 4 days, but I didn't start on it until the beginning of 4 days before that. And that was urging by Theo, who's pushing me to finish that. So unlike AMD 64, where things just kind of worked the first time, i386, people started having weird problems. And a lot of this can be attributed to old legacy crummy hardware, but it turns out some real bugs were discovered. So AMD 64 does not use the machine BIOS for anything after we're done booting. We don't explicitly call and use the BIOS for any purpose, but i386 does. It uses the BIOS in a number of different places, and it uses it at times when you can't predict. It's just very odd. So things that we had aggressively NXified all of a sudden needed to be executable. And that meant that we had to go and remove some of those permissions, which is unfortunate, but that's what, life's tough. So those things that we had to relax sat in a region of memory called the ISO hole. ISO hole is a memory that goes after 640K and goes up to 1 meg. And the machine will put BIOS ROMs there and the VGA scroll buffer and stuff. If you think about it conceptually, for AMD 64, none of that stuff is ever executed. So we kind of copied the same model we used with AMD 64, and we just made that whole region not executable. Well, on i386, there's BIOS goo there that needs to be executed, so we had to go put that permission back in. So on the whole, i386 is now at the same place AMD 64 is with a slightly wider executable region. So AMD 64 is pretty much complete. From what I can tell, this is kind of where we're at now. We have userland WXORX, which has been there for a long time. We have kernel WXORX now with the stuff we've done earlier this year and late last year. If somebody finds a mapping that's wrong, I'd love to know about that. So I view this as an ongoing effort. i386 is mostly complete. We have userland WXORX as well. We left in our old line in the sand mode, and what that is a very old way of doing userland WXORX for i386. So that deals with segment permissions and segment limits and stuff. The reason we chose to leave that in there is, again, we have legacy users that have hardware that doesn't support NX. So what that means is we could either remove that old model of protection or just leave it in and let them use it. We actually have 2 levels of WXORX protection in i386 now. It's actually more robust than AMD 64 in that regard. There's a few lingering BIOS bugs like I just talked about, and I haven't done the trampoline split for i386 like I talked about earlier, so I'll have to do that at some point. So this was supposed to be a 1-month effort. How hard could that possibly be? And again, I viewed it as a correctness fix. So it wasn't like a security errata needed to be posted or something. This is an iterative, continual improvement. What do you guys think about that last question? So after we'd finished AMD 64 and turned on WXORX, how many violators do you think we found in OpenBSD, like OpenBSD violating its own page permissions? For example, executing data or executing the stack or something like that. And that was very disheartening because I expected to see things spectacularly blow up. That's a testament to the quality of the tree. I'm not saying that there's not possible that someone else out there had derived an exploit that did something outside the bounds of OpenBSD, but when we flipped the switch to turn on WXRX, nothing broke. And that was, again, disappointing because I expected there to be a lot of aha moments. i386 had a couple of these other problems like we found, like the BIOS trying to execute, but yeah, we found none. So keep in mind, and again, this is, I'm not trying to pitch this as a security improvement, but nothing is a silver bullet. As Theo likes to say, everything's a copper bullet, a lot of them. So this is another way that we can improve what could happen in the kernel if somebody was able to get in. Now, you pretty much have to do kernel ROP now in order to do anything bad in the OpenBSD kernel because everything is locked down. You've got like maybe 3 or 4 instructions you get to play with. You won't be able to go and manipulate the page table anymore because we've locked everything down to a great extent. So nothing's a silver bullet. It's a cost analysis. The cost on this one's really low. The performance overhead is 0. i386 switching to the new PMAP model, the performance overhead is maybe like 0.02% or something. It's really, really quick. Most of the modern processors are really advanced in the way that they read that page table format now. So the model is it's cost analysis and the cost is low. So that's all I've got. Thanks everybody. We're a little bit early for dinner, but I guess that's okay. I'm happy to take any questions, or if you have some questions, you can shoot them there too. Yeah. So I think the way I understood your question was, do you foresee any time we might remove the older architectures? Yeah. So I'll give you my personal take on it. OpenBSD is an operating system that's built kind of for the developers. So the answer to when we remove support for something is when nobody has any interest in it anymore. I don't see, and we have removed architectures, and we removed a couple this year. I don't see i386 going away. There's just too much interest in it. The other thing that's interesting about keeping other platforms around, like people ask, why do you have VAX still? Why do you have 32-bit Spark? Those platforms find bugs. Nobody's running OpenBSD VAX in production with anything, as far as I know. But having that code around keeps us honest. I was working on the hypervisor this year, right? I have built a hypervisor for i386. Who does that? But it found bugs. And again, it's run it through its paces, make sure everything works. Again, platforms get removed when no one has interest or when the hardware becomes so hard to find that nobody can get it. And neither of which I see happening with i386. I'm sorry, can you repeat that? I don't think that, I don't really know how to answer that question. I think my take on it would be, you'd have, I don't see people saying that of retiring a platform for security reasons. We do have architectures that don't have any WXRX support as far as from the hardware perspective, but we don't refuse to run on them. We just take advantage of the capabilities that are there. Well, on i386, we increased the code somewhat because we have a second PMAP now, but that code kind of was already there. The size of the number of lines of code is almost identical. I think to do all the split of the kernel regions that I was talking about earlier was maybe 10 or 20 lines of assembly. It wasn't that bad. And some linker script changes. The footprint of the code does not grow appreciably with this model. It's a good question. All right, thanks, folks. Let's go have some dinner.